All right, welcome back. We're going to start on question 39 here. The structure of sorbic acid can be represented by the following line diagram. Sorbic acid is classified as some type of compound, and the rate of its reaction with bromine, Br2, is predicted to be what? All right. Column I is going to fill in this blank with saturated or unsaturated. We see in this compound here that we have carbon-carbon double bonds, which means that this is an unsaturated compound. The carbons don't have the maximum number of hydrogens. They're not saturated with hydrogens. So we are going to cross out row A and B because this is an unsaturated compound. Now we have to figure out if it's going to have a fast rate of reaction with bromine. This is a test of unsaturation. If you add bromine, a bromine solution to unsaturated compound, bromine will quickly react with unsaturated compounds via addition. Now, this is a common test for unsaturated compounds. Bromine, in its aqueous form, is kind of like an orangey color, and then once it's added onto the unsaturated compound, most organic compounds are clear in color, so the solution will just be clear. So it will go from orange to clear. It's a fast reaction. It's going to react spontaneously. All those sort of words here. Another way that they might ask this question is if you mixed this compound with a solution of bromine, what would the final color of the solution be? And then instead of saying fast in this compound, you would say it's going to be a clear solution, not an orange solution, because the bromine will have all reacted with the unsaturated compound. Some molds detoxify sorbic acid by converting it into other compounds. Two of these compounds are represented by the following line diagrams. Compound 1 can be produced from sorbic acid in what type of reaction, and compound 2 can be produced from sorbic acid in what type of reaction? Well, the difference between compound 1 and sorbic acid, we'll redraw that sorbic acid in here from above. The difference between compound 1 and sorbic acid is that we have one less double bond, which means that we had to add something to the double bond. We had an addition to the double bond. That's how we would get from this sorbic acid to compound 1. Compound 2 no longer has a carboxylic acid as its functional group. Instead, this is a carbon at the end here. This is a carbon, so this would have been added with an esterification, because we have changed our functional group to an ester. So we have an addition and we have an esterification. An elimination reaction is where you eliminate a functional group and create a double bond. In a substitution, you would be swapping out a functional group for a different functional group. Next question. Codeine, a sedative and analgesic, is present in several types of painkillers. Codeine is a weak base that can react with water, as represented by the following equation. Here's our Bronsted-Lowry equation with a Kb of 1.62 times 10 to the negative 6. The equilibrium law expression for this equilibrium reaction is Kb equals the hydroxide concentration times our conjugate acid, and all over the concentration of our weak base. In the reaction represented above, the species that act as Bronsted-Lowry acids. Bronsted-Lowry acids are our proton donors. Now, in the forward reaction here, it is the water molecule that donates a proton to the codeine molecule. And in the reverse reaction, going this way, it is the codeine's conjugate acid that donates a proton to the hydroxide to make the reaction go this way. So our two proton donors are water and the conjugate acid of the weak base codeine. Here's our conjugate acid. I'm going to just highlight it and write it, the conjugate acid. A 0.100 mole per liter solution of codeine will have a concentration of hydroxide ions of what? Here's an ice table question. Normally I write out the reaction here, but this is a large molecule to write out, and the reaction is just above. So our initial concentration of, I will write out the reaction. Don't be lazy, Kyle. So I'll write out our reaction here. Here's our codeine plus our water is going to form our hydroxide and our conjugate acid. Water is not going to be involved in this ice table. It's not involved in the equilibrium expression. Its concentration doesn't really change. It's the solvent. Our initial concentration is of our codeine is 0.100 mole per liter. Our initial concentration of our hydroxide and our conjugate acid is 0. This is going to change by x, and these are going to increase by x. Now, for these weak acid-base ice table questions, we assume that the change is so small because the Kb value is such a small value, it's times 10 to the negative 6, that it is practically negligible for finding the equilibrium concentration of our codeine. So I'm going to rewrite the equilibrium concentration of codeine as just 0.100. I'm going to say that x here is, we're going to assume, very small. So it's not going to really make an impact here. But we do want to find out what x is, and the final concentration of our hydroxide and our conjugate acid is going to be x. Our equilibrium expression, Kb, is going to be our concentration of our hydroxide times our concentration of our conjugate acid all over the concentration of our codeine. Well, we know what our Kb value is. It's 1.62 times 10 to the negative 6. And we know that our hydroxide and our conjugate acid values are each x. So it's going to equal x squared divided by 0.100 moles per liter. To solve this question, we'll multiply this up, and then we'll take the square root. So x is going to be the square root of our Kb, 1.62 times 10 to the negative 6, times our concentration of our weak base. If you're tracking the units, really you'd get moles, square root of moles, square root of liters, but we'll treat it as the Kb. If you calculated the units as well, the units would cancel. You get moles per liter. So we'll put this all into an expression, the square root, and then because it's in scientific notation, I'll put in brackets 1.62 times 10 to the negative 6 times our concentration of our base, 0.100. Put that in, and then we're going to end up with an answer that looks very similar to B. That's our concentration of our hydroxide ions, B. Next page. Use the following information to answer numerical response question 15. Here we have I think these are all variations of citric acid. I believe that's the formula that matches here. Yes. With different Kas. Match the species numbered above with their descriptions given below. There's more than one correct answer. The species that is both polyprotic and amphiprotic. So remember, amphiprotic means it can be both an acid or a base. And poly means many. It can accept or donate more than one proton. We'll answer this first one here. So the ones that are amphiprotic are the ones that are going to have hydrogens that they can donate, protons they can donate, as well as a negative charge to show that they can accept protons. The acidic protons are combined with this organic acid group. This is a carboxylic acid group in brackets here. So substance number 2 here has 2 acidic protons because there's 2 more of these carboxylic acid groups here. And substance number 3 only has 1 acidic proton. But substance number 2 also has a negative charge. Substance number 3 also has a 2 negative charge. Both of these substances, 3 is polyprotic because it can accept 2 protons. 2 is polyprotic because it can donate 2 protons. 1 is polyprotic because it can donate 3 protons, but it's not amphiprotic because it cannot accept any protons. It doesn't act as a base. So 2 or 3 can fit in this first blank. The species that is the conjugate base of this acid is what? Well, if this is acting as an acid, then it would donate a proton, and it would end up as 3 as its conjugate base. The species with the weakest conjugate base means that you are the strongest acid. The strongest acid. If you have a weaker conjugate base, you will be a stronger acid, which means it will be the biggest Ka. The largest Ka is right here. This citric acid, this first one, this is our strongest acid. So 1. And the species that will form a buffer when mixed with an equal amount of citric acid, species number 1, is what? Basically, what this question is saying is, what is the conjugate base of citric acid? Because a buffer solution will be an acid and its conjugate base. If you were to lose 1 proton from citric acid, and then you form this dihydrogen citrate anion, then this is our conjugate base. So the buffer solution would form if you combined it with number 2 here. So we got 2 answers to this one. It could be 2-3-1-2, or it could be 3-3-1-2. Almost at the end here. Limestone rocks, calcium carbonate, present on the seafloor react with seawater to establish the the carbonate and the bicarbonate buffer system on the seafloor. The equation that represents the reaction of hydronium with the buffer on the seafloor is what? And the effect of the buffer is to do what? Now, the hydronium here is going to react, because this is an acid, with the buffer's base. Here's our buffer system that we've established here. The buffer system that we've established here is that the bicarbonate anion is acting, or the hydrogen carbonate anion, whichever way you want to say it, is acting as our acid, and the carbonate anion is acting as our base. This is our buffer system right here. The whole purpose of a buffer system is to maintain the pH of the seawater. So you can eliminate the ones that say that the purpose of the buffer system is to decrease the pH of the seawater. Yes, these both act as bases, but the point of them in their concentrations is to resist pH change. They both can act as bases, I should say. So decrease is not the thing. Also, if you were to decrease the pH, then you would be becoming more acidic. Then you're choosing which one is it going to react with. Well, this is the base of our buffer system, the carbonate. So we're going to choose the reaction where we react with the base of our buffer system. Now, if the buffer system was carbonic acid and the hydrogen carbonate anion, then you would react with hydrogen carbonate. Yes, this can act as a base, but within this buffer system, it's the acid. So if you were adding acid to this buffer system, it's going to react with the conjugate base of the buffer system. A sample of rain was collected and the pH was measured to be 5.400. The hydroxide concentration in the sample of rain expressed in scientific notation is A.Bc times 10 to the negative D moles per liter. Okay, now some pH formula stuff. There's two ways to really go about solving this. You could go to a hydronium concentration first and then change to a hydroxide concentration, or you could go to a POH and then change to a hydroxide concentration. Both ways will get you the same answer. So you could do 14 minus pH gives you POH. So I'll show that way first. You do 14 minus 5.400, and you will end up with a POH of 8.600. And then you can do 10 to the power of negative POH will give you your hydroxide concentration. So we can do 10 to the power of negative 8.600, and we will get, I will pull it up here. We can turn this on. We will do 10 to the power of negative 8.600. And we have three significant digits because of pH sig dig rules, but you get 2.51 times 10 to the negative 9. 2.51 times 10 to the negative 9. So our answer here would be 2519. You don't really have to worry about significant digits because they tell you that they want it to this many significant digits. That's one way of going about it. So you did 14 minus the pH to get POH, 10 to the power of negative POH. You could also do 10 to the power of negative pH to get hydronium concentration. My writing's getting worse as the video goes on. And then you could do Kw divided by hydronium concentration to get hydroxide concentration. And I'll just show you that on my calculator here. So the first thing we're going to do is we're going to do 10 to the negative pH, so 10 to the power of negative 5.4. There's our hydronium concentration, and then we're going to do Kw, which is going to be 1.0 times 10 to the negative 14 divided by our hydronium concentration. And you get hydroxide concentration, which gets you the same number, 2.51 times 10 to the negative 9. Either way of going about this question will get you the same answer. Check your calculator mode. Some calculators have like an engineering mode or a science mode that kind of estimates or rounds for you when you do 10 to the negative pH or POH. I'm not sure why it does that, but it's a good thing to practice trying to get this same number on your calculator by both methods. Here's a titration curve. In the titration represented by the graph above, the titrant that is added to the solution is what, and the sample is what? All right. Our sample is starting at a basic pH. So our sample is going to be a base. I'm just going to write here that the sample starts basic. And then we are adding titrant on our x-axis here, and we're becoming acidic. So our titrant must be an acid. And then we'll take a look at the question. The statement above is completed by the information. Is it a base? Is it an acid? Well, we've decided that the titrant is an acid because as we add titrant, our pH decreases, becomes more acidic. And then the sample is what? Monoprotic or polyprotic? We can tell this by the shape of the curve. We have two endpoints. We have two endpoints, and we have two buffer regions. We have two endpoints and we have two buffer regions, which show that we are going to have two separate reactions, two quantitative reactions as we go throughout this, which means we are polyprotic. It's an acid and the base is accepting two protons. We have two reactions, two endpoints, two buffer regions, two reactions. therefore polyprotic. And I believe that is our last question for this practice diploma. I hope these videos were useful. If you didn't know how to solve a question, then now you have the information to do so. Good luck on your Chemistry 30 diploma. You're going to do great.